Hey students, let's give another go at another hard problem. And again, not surprised, a lot of people are asking about this. These are really, really, really hard. And I guess I got overzealous and overexcited with these problems from the university physics book. The curriculum does require me to give you some calculus ones, and so that's what this is about. But these are some hard ones, and that 79, that 80, the 82, and hopefully you got a chance to watch those. But let's give this one a shot. Number 74. It's about in inductance, and it's talking about twin lead, or sometimes antenna lead wires. It's called. It says two long parallel wires, and so let me take wire 1 and wire 2 and kind of picture them going back into the board, thinking like a lecture, but back into my paper or back into the screen. And so these are what we call twin leads. Do I have any twin lead? You know, we don't use twin lead. I'm here on my electronics desk, and I'm wondering if I don't really have a twin lead around here. That's too bad. I got a bunch in my garage. Use it a lot. Let's see. No. All right. I thought maybe I had some in the back drawer there. Used to have a bunch because, you know, I used to have an antenna and a bunch of other stuff. Anyways, but I don't think this is too hard to imagine. Twin lead wires. So two wires, but it says two long parallel wires carry equal current in opposite direction. The radius of each wire is A. So I'm going to put A. And so maybe I'll say the current goes down here. And so the current goes down and, you know, goes through some kind of probably electronic device, like a TV reception, and comes back, you know. And so the current is being generated by an antenna out here. And so this would have radius A also. The radius of each wire is A. And the distance between the centers is D. Okay, and so they're separated by a distance D. It says here, show that if the magnetic flux within the wires themselves can be ignored. Okay, so we're going to ignore, and I'm glad they say that, because that would actually be the hardest part of this problem. And I don't think we've given you the skills, this would be for the engineering class, to even do the flux within the wire itself. So I can see why the author is saying that. Okay, show that the magnetic flux, show that if the magnetic flux within the wires themselves is ignored, the self-inductance of the length L, and so we're going to say that this long wire has length L, or could actually be longer, but within a section of length L, such that this is the inductance. Okay. They give us a hint. Calculate the magnetic flux through a rectangular length L and between the wires. So the hint is saying, what is the flux here between the wires? But not within the wires. Now, maybe you can see conceptually the physics here, and that is the flux created by the current itself actually opposes the current itself. And that's what we meant by inductance. You might remember the chapter on AC currents. Let's see, what was that one? I'm looking here at the book. Oh, well, it's also in this chapter. Okay. And in this chapter, we said that there was a reactance of an inductor that depended upon its frequency and the inductance. And then the current would be the voltage divided by, and it's the total impedance, but part of that impedance is the reactance of an inductor. So in other words, if you're trying to get current to go through this, which, this current is pretty small, we would just have an antenna sitting up here, and we're trying to get enough current here to, drive a TV receiver or some kind of receiver, maybe a rangefinder, who knows. But we really would like this inductance to be on the small side, or if we were turning it off. In today's world, we're more digital. And so we'd be turning it on and off. And so if we were sending data down here, on, off, on, off, on, off, on, off, we want the current to be able to, go on and off kind of quickly. And to get it to start up or to decay away is affected by that inductance. That was that LC circuit stuff. So, LR circuit stuff. And what I'm trying to get at then is inductance is going to be a really bad thing if you want to turn things on and off really quick. And in today's world, where we're all connected to the internet, we want our data rate as high as possible. And this design is terrible. You take two wires right next to each other like this, they induce an inductance within themselves, and you just can't get the data very quickly. And so these old twin lead stuff have been, they're gone. The old telephone wires were like this. They were just two twin leads gone. In fact, here on my workbench, I do have, here, is a more modern USB-A connector. And you look down inside, you'll see there's 4 connections, and 2 of those is for power and 2 of those is for data. And in order to deal with reducing the flux, they twist them. And so they're rotated inside. And so here, if I untwist it, you'll see the 4 wires here. But what's really nice about that is that when you twist it over, the flux undoes itself, kind of like a stitch, goes one way and then the other. And now you can put data down here much, much, much faster. And so these USB, it doesn't matter if this connector's an A or B or a C, but the twisted lead really helps this problem. Anyway, so I don't know if that helps you to try to understand the problem or why we would care about it, and even ways to mitigate the problem. But this is really what they're after here. And they give us some helpful hints here. You calculate the flux through this. So we're going to make a little rectangular loop. And in fact, this sounds an awful lot like what we did here in number 79, where we had a rectangular loop next to a wire and we calculated the flux. And if you remember this one, I might even still have the answer somewhere in this pile of messy papers I have. But I believe this was it. This is the flux. So let's just kind of repeat number 79. And I'll do it for just one wire for the moment, and then we'll just double it at the end. But let's go ahead and do a lot like we did right here. This was our answer on page 2. If you watched that video, here's what it is. And in fact, maybe because some of these videos are so long and I'll bore you guys, why don't I just run through this and use that as my answer? Okay, so if I have a wire and I have a rectangular right next to it, and now in this case, number 79, we gave a little space, X. But in our case, our little space would be A. And then it goes out to B, but in our case, for this problem, it would go out to this edge, which would be D minus A. So let's talk about that. But as you review this number 79, you'll see that what I said is to get the flux, is you got to take the magnetic field times the area. But the problem is the magnetic field gets weaker according to this equation as you get further away. And so you have to take the rectangle and cut it into strips and say, all right, let's take each strip thinner and thinner. So it would be the magnetic field times the area of one strip, and then you would add up all these little strips. And then if you take the limit as that area goes to 0, in other words, each little strip gets thinner and thinner, you would have something that would look like this. The limit as the area goes to 0, and the area of each strip would be its length this way and its width this way, which they call delta x. And then when you take the limit as the delta x goes to 0, that is, as these strips get thinner and thinner, you're going to get this integral. And maybe that's a good place for me then to kind of start with this particular problem. I'm going to say then the flux from this one wire is an integral, and it would be the B field caused by this current, I, which is going to change with distance. We'll add that in here, down here. And then it would be this length of the rectangle, which for our problem, we're going to say is L. And I'll still call this movement along here X. And so I'm taking little strips like this. And my B field would be mu naught times I over 2 pi x. And that's, again, what we did in number 79, where we said, what is the magnetic field for my wire? We wrote it as mu naught I over 2 pi r, but r is the distance from the wire, so we wrote it as an x. And then it's the L, and then it's the dx. Now, again, in 79, we said the distance the rectangle was away from the wire was a distance of x. But for us, in our problem, our little rectangle starts at a distance of a. And we're going to keep going along the x-axis, calling this the origin. Okay, so we're going to start at x equal to a. And we're not going to go all the way to the center of this wire, which would be a distance of d. We're going to just go shy of that, because we're not going to go into the wire. We're going to cheat ourselves a little bit. But, like I said, hard enough. And so this would be a d minus an a. And so this would be a mu naught, an I, an L. Those three would be a constant. And the 2 pi, we can pull those out, and then we would have just this integral that we've seen quite a bit in these last few problems, and then going from a to d minus a. And so then this would be mu naught I L over 2 pi. The integral of this is natural log of x, and it's going to be evaluated from a to d minus a. So this would be a mu naught I L over 2 pi, and then we would have natural log of d minus a, excuse me, minus natural log of a. Now if we take advantage of the property of logarithms, which in 79, for anybody who's watched that one, you know, I didn't do that. Where's that page 2? 79, number 2, I got to the end. Oh, and I realized after I left the video that I dropped the minus sign. I put a plus sign. So if you watch that one, there's a little mistake at the end. It was minus sign, and I missed that. And anyways, it should have been there. But I did notice that after I got done with the video, I noticed that the author gave a common denominator down here. And he wrote down here as x times x plus b. And then that, of course, would make an x, and then you would subtract off an x minus a b, which would just leave a b here and then an x. So maybe that looks better when you put it together with these other factors. So that's what they did in 79. But what I didn't do is take advantage of the property of logarithms in this one, although I did it in another problem. I think that was 82, where I said, let's take advantage of this. Yeah, it was, because that was that real hard one with the velocity of that wire. But I'm going to take advantage of the properties of logarithms, and the difference between two natural logs is the same as their quotient. And so that's the flux from just one wire. So let me then say, if it is two wires, so I'll call it total, I'll just double it. And when I multiply by 2, that 2 in the numerator will cancel with the denominator, and then you'll just get this ln d minus a over a. And believe it or not, we're almost done then with this problem, now that we've kind of used number 79 as a springboard. Let's see. I lost this one. It's number 74 here. Because it helps us by saying, use this principle that the inductance is the number of turns times the total flux divided by the current. Well, the total number of turns is just, one set of twin wires, so that's just a 1. And the total flux we just did, but when we divide it by a current, so that'd be 1, and then we get a mu naught, and then there's the I that's going to cancel off with this I, and then the pi, and then the natural log of d minus a over a. And then the currents will cancel off, and it's mu naught L over pi ln of d minus a over a. And I think that's what they have. Yeah, show that the inductance is this. Yay! So it took us a while to kind of get there, although much sooner than I expected, because I kind of piggybacked off of number 79 here. But there's our inductance for our twin lead, which, for any of you old enough to work with these twin leads before the modern coaxial cable, this comes out with the dimensions of the D and the A purposely to be 300 ohms per meter. So we'll move the L to the other side. So if you take the twin lead and you stretch it out, 1 meter, you get your 300 ohms per meter. And today's coaxial cables run a little different. That's why if you've ever had lived in a world where you had to connect a twin lead together with a coaxial cable, you get this adapter. Terrible picture. But this adapter that is supposed to match the 300 ohm impedance with the 50 ohm impedance. Otherwise you don't get a good signal here. And I remember having this problem where our new cable system came into town. Hey, we got a cable, but we had an older TV that was still 300 ohms, so we had to get the impedance matching equipment. Anyways, I digress, and hopefully that was a fun calculation, but a challenging. These 4 are really, really challenging, and I wonder if I should really even include them in the homework. This was just a little bit too much and over the top, but hope the video nonetheless helps a little bit somewhere. Know this, that nothing on the test would be this hard. This is certainly at the engineering level, and this is just too much to ask on a time test also. So that being said, learn the physics, and hopefully you'll see how it applies to you in the life science, not so much in the engineering field. All right, take care.